Yes, we can hear you.
Okay, very good.
Can you hear us?
Yes, we can hear you. Okay, I guess it's working. It's working now. The camera doesn't seem to be working.
Camera doesn't work.
I don't see the camera here.
We didn't start our video.
Ah, okay. Okay. Okay, then now it's good. Yeah, I think it's fine.
No, it's fine. We
Yeah,
wanted
yeah,
to
it's
get
fine.
rid
Just
of this one.
minimize this thing. No,
I
yes,
can
yes.
just. Okay. That will be correct.
It will come, no?
Yeah.
Okay, perfect. I think we can start now. And hello, everyone. Welcome to the third lecture or the third meeting of this seminar in computer architecture. Today is my turn to talk about something happened.
Are we sharing? Still sharing screen?
Not sharing.
Can we not use the camera, or can we use the laptop's camera for now?
Okay.
Okay, because it started when we turned the camera on.
I mean, I don't need to use the camera anyway.
Now you need to press escape once so that you see the.
Okay, let's share again. This thing, hopefully.
Desktop 2.
Desktop 2.
First start the
Oh,
presentation.
yes. This one.
Wow.
Camera is working, supposedly. Okay, I hope it's working well now.
I mean, can't you use some camera so that people can see something?
Yes, I turn on the laptop's camera, but it doesn't seem to be working.
It was actually fine with the other camera.
No, then we lost the screen.
I think using the two laptop was better because sometimes overload the Zoom.
Yeah, now you can see at least one.
Okay. Okay, yeah, I think I can continue now. So, yeah, welcome everyone to this third meeting of the seminar in computer architecture. I am Juan Gomez Luna. I'm one of the instructors of this course. And today is my pleasure to talk about one topic where I'm doing active research, not only I'm alone, but with many other people in the Safari research group, which is memory-centric computing. I think it's a really exciting topic that it's a way of potentially solving one of the key issues and key bottlenecks in computing systems these days. This bottleneck is the access to data. And that's why we can say that computing is bottleneck by data, is bottleneck by the data movement in the system, by the need for moving data all the time between the storage and the memory units to the processing units, to the processing elements in our systems. But we know that data is key for all important workloads these days, such as artificial intelligence, machine learning, genomics, etc. And all these important workloads are very much data intensive. So they require rapid and efficient processing of large amounts of data, but this data is increasing more and more every day. And as for an example, I can show you this plot for the exponential growth of neural networks, where you can see how the size of networks has evolved in the last couple of years, basically. For example, if you look at the one that is highlighted, the GPT-3 is like how much? More than 100 times more data, right? 100 times larger than the previous generation, than GPT-2. So this is just for an example. By the way, the slide comes from one talk that Sean Lee, who is one of the founders of Cerebras. This talk was delivered last year as a Safari Live seminar, and Cerebras, as you may have heard, is a company that fabricates huge chips, wafer scale accelerators for machine learning and neural networks. Okay, so as I said, data is a huge, or the access to data is a huge issue or bottleneck for most workloads and computing systems these days. And but at the same time, it's key for the workloads, future workloads such as current and future workloads such as in-memory databases, graph or tree processing, in-memory data analytics, data center workloads, etc. So all of these are bottlenecked by the access to data, and this causes performance and energy bottlenecks, undesired performance loss and undesired energy consumption. And it's not only these server-grade workloads that you see on the screen, but also in consumer workloads that we can use in mobile devices, such as laptops or cell phones, such as the ones that you can see on the screen. There are recent studies showing that these as well are bottlenecked by the access to data, and that causes performance and energy bottleneck. And even more, in our group, there is a lot of active research on genomics, and genomics is also a very good example of the exponential growth in the amount of data that needs to be processed. Especially if you look at the plot on the left-hand side, you'll see that at some point, sequencing technologies became much cheaper, and that made that the amount of, or the number of genomes sequenced increased very much significantly over time. Like for example, here in 3 years, in just 3 years, you can see increase of almost 8 times. So very large increase as well in the amount of genomic data. And this affects everything, and it's really important in the genome analysis pipeline, because after sequencing, there is a lot of processing to do, and this processing is costly. It requires a lot of accesses to memory, to the storage, in order to read the to load the reads that correspond to a particular individual, and also access the reference genomes that, like for example, the human reference genome that you need to do read mapping, and also later steps such as variant calling. So this process as well is bottlenecked by the access to data, and this causes a performance and energy bottleneck. If you want to read about the challenges and the opportunities in genome sequencing, I would recommend you this relatively recent work from our group on nanopore sequencing, which is one of the newest technologies for genome sequencing. But here as well, you can find a lot of performance and energy bottlenecks due to the access to data. And even though, as I said earlier, sequencing machines became cheaper, and the generating sequencing data or genome data became cheaper and faster, still processing that data, doing all the necessary data analysis is extremely slow. And that's why we need to accelerate these workloads. But of course, we'll have to take into account the data movement bottleneck that we are discussing today, right? And what you see here on the screen applies not only to genome analysis and to genomic data, but also to many other data generators and analyzers. So it's important to figure out ways of accelerating all these processes. That's one of the things that our group discussed, led by Mohammed Alser. You know him as well, because I think he was teaching last week. What they discussed in this summary work, Accelerating Genome Analysis, a primer on an ongoing journey. And as an example of work that tries to accelerate modern workloads, and in particular genomics workloads, I can show you this one that we published a couple of years ago, an FPGA-based near memory acceleration of modern data-intensive applications. This includes interesting applications such as pre-filtering, the sticky snake filter that probably Mohammed introduced last week, but also other applications such as weather modeling, climate modeling. So, in summary, data overwhelms modern machines, and this affects storage and memory capability, communication capability, basically this data movement that we are talking about, and also computation capability as well. And this greatly impacts robustness, efficiency, energy efficiency, performance, cost, etc. So if we think about the communication cost, part of the issues come from the way that the computing systems are designed, not currently, but already for many, many years. John von Neumann, who is there in the picture, and by the way, it's pretty likely that he studied in that building over there, proposed this model for a computing system where you can see the memory and the storage unit on one side, the computing unit on the other side, and something in between that is a communication unit. There is nothing wrong with this model by itself. The problem is when this communication unit is very narrow, because in that case, it's going to behave as a funnel, right? You want to access data from here, read data from here in order to operate on it here, and then you want to write results back to the memory and the storage. But if this communication unit is very narrow, it has low bandwidth, and it has high latency, then you really have a problem, because the access to the data is going to be the main bottleneck of your system. So here you see the computing unit. But over the years, computer designers, designers of computing systems and computer architects have been trying to propose and figure out solutions to deal with all this data movement, with all these narrow communication channel. And an example of that is that if you look at some pictorial representation of the internals of a multi-core CPU, such as the picture that you have on the screen, you will see that most of the area of this processor is devoted to memory, either on-chip memories, as we can see, the shared L2 cache, the shared L3 cache, or access to memory, right? Like, for example, these shared memory controllers. And these memory controllers are designed to access an external shared memory, and as well as some storage, so storage devices. So as you can see, most of the system is dedicated to storing and moving data, but still the system is bottlenecked by the access to data. And this is not just in this pictorial representation. If you look at the any modern CPU, for example, this one from AMD from 2020, you'll see that most of the area in this chip is devoted to memory, right? So most of it is occupied by the L3, as you can see in the middle of the picture. Or in this slide, we have another example. This one is a little bit more recent, from 2021, where AMD increases the L3 size by placing one layer of L3 on top of the processor, as you can see. Well, you can see it here on this left part of the picture, but also right here in this 3D representation that is pretty nice. And not only AMD processors, of course, similar things you can observe in IBM processors. For example, this is an IBM Power 10 from 2020. Also, most of the chip area is occupied by L3 and L2 memories. Or even more recent is this one, this M1 Ultra from Apple from 2022, where, you know, here inside the processor chip itself, there is a lot of SRAM, L3, L2, as we have just seen in the previous pictures, but also there is a lot of the entire system that is occupied by DRAM or by storage. So as you see, even though most of the available space in the system is devoted to storing and accessing data, still systems are bottlenecked by the access to data. And this overwhelms modern machines. I mentioned earlier some consumer workloads that you can find in cell phones or you can find in laptops. They are bottlenecked by the access to data. And just for an example, and this is from a relatively recent study from our group, 62.7% of the total system energy is spent on data movement in these consumer workloads from Google. So ideally, we should be able to design intelligent architectures that handle data well, right? That's what we really desire. And how to handle data well? First of all, ensure that data doesn't overwhelm the components. I don't know if there is an issue with live streaming. It seems that there is an issue with live streaming. Can you check? So what I was saying is that how to handle data well. First of all, ensure that data doesn't overwhelm the components. Ideas to do so is first design intelligent algorithms, design intelligent architectures, and also do whole intelligent system design. How to do that? By co-designing algorithm, architecture, and devices. That would be ideal in order to handle data well.
We're seeing something weird on Zoom.
Yeah, I on Zoom and probably on YouTube as well. No, I mean,
yeah, it's flipping between slide 3D last level cache and
yeah. I noticed.
You should redo the sharing.
I thought I was checking.
These multiple desktops really confuse all of these things, I think.
Okay. Let's start sharing again, no? You think it's fixed now?
Yeah, it looks better.
Okay.
It's slide 26, right?
Yes, exactly.
Okay.
Okay, so yeah, so what I was saying is that we should design intelligent algorithms, intelligent architectures, and basically co-design the algorithm, the architecture, and the devices. And we can also take advantage of the vast amounts of data and metadata that the systems handle. Because if you understand data well, you will be able to improve architectural and system level decisions. And that's what is luckily done more and more with new designs and intelligent architectures. And we are probably going to cover some of these designs and how to apply machine learning and intelligence to computer architectures in different parts of the system. So, but in order to do so, we need to understand and exploit the properties of different data to improve algorithms and architectures in various metrics. So, problem with computing systems today is that they are processor-centric instead of being data-centric. They are made based on designer-dictated decisions instead of data-driven, and they are also component-based. So they are also based on component-based myopic decisions instead of data-aware decisions. So key points or key ideas to build intelligent architectures, intelligent machines, is to make them data-centric, data-driven, and data-aware. And we are going to talk about at least one of these three pillars in today's lecture. But if you want to get an overview of how to build intelligent architectures that handle data well, I can recommend you this short paper from Professor Mutlu and also the related tutorial. But in order to enable all these changes in computing systems and make them more intelligent, we need to revisit the entire stack. As I said earlier, it's important to co-design the algorithm with the architecture and with the hardware itself, with the devices themselves. And this requires, first of all, a change of mindset in many, many people, in many, many designers. Today, we are mostly going to focus on one of the three pillars, as I said, how to build architectures that are data-centric or memory-centric. Data-centric architectures have certain properties, such as the ones that you can see on the slide. First of all, they process data where it makes sense or where the data resides, and that can be done by using processing in memory or processing in near memory structures. These data-centric architectures can provide low latency and low energy data access, which is really desirable to make the systems more efficient in terms of performance and in terms of energy consumption. They should provide ways of storing data in a low-cost manner, but also do it fast enough. And there is where, for example, hybrid memory systems or hybrid storage systems can help a lot. And especially if these hybrid memory systems or these hybrid storage systems are handled by intelligent controllers that can make the right decision of where to place data. For example, if data is cold, let's say is not very frequently used, you can probably place it in a slower memory that at the same time will be probably higher capacity, right? But at the same time will be probably cheaper. But if you have data that you're going to use very, very frequently, you probably prefer to place it in a more expensive memory that at the same time is faster and probably will be smaller as well. That's just to give you an example. And another characteristic of data-centric architectures is the ability to manage data in an intelligent way. I was mentioning intelligent controllers related to hybrid memories and hybrid storage, and I think I already gave you one good example. Another example, and I think that I have a later slide to talk about that, is how to deal with security issues, security vulnerabilities, such as, for example, the RowHammer phenomenon that can happen in different chips and causes that certain bits are flipped. And due to these bit flips, there are vulnerabilities that appear and security threats. If you have an intelligent controller that is able to identify, an intelligent DRAM or memory controller that is able to identify when one particular application might be an attacker because it's trying to produce these RowHammer bit flips, it's trying to cause these RowHammer bit flips, then this controller can probably throttle the accesses from this attacker, right? From this application that may have bad intentions, let's say. Okay, but let's gonna start from the beginning. Process data where it resides or where it makes sense. So as I said earlier, a lot of the system is already occupied by memory, DRAM, storage, or even sensors. Processing where it makes sense means providing these components of the system with certain amount of compute capabilities. Maybe not in all cases you are going to compute in the storage, or maybe not in all cases you are going to compute near DRAM or inside DRAM. You're going to use it when you're going to do that when it really makes sense. But think about, you know, the large amounts of data that we typically keep in the storage, right? We are talking about gigabytes or terabytes of data. We are not using all that data at the same time, right? But even more, we may need to use, we may need to access part of the data that we keep in the storage, which may represent gigabytes of data, but perhaps we only need to check if that's the data we want or not. Imagine that, imagine that you have a database in the storage and you want to perform a query on certain elements, certain entries in the database. What you would need to do is probably checking some indices or some particular value of each of the specific entries, and then those are the only relevant ones, right? Those are the only ones that you want to move closer to the processor because you are going to use them for further computation, for later processing. So one potential way of getting rid of a lot of data movement and unnecessary energy consumption would be to place certain compute capability here in the storage. And when someone says, I mean, I'm saying storage, but I could say DRAM or I could say sensors as well. We could filter a lot of the data that the sensors are capturing from the environment, and probably most of the times is completely useless, right? If we can identify what data is useful or useless near the sensor, we would be saving a lot of a lot of cycles and a lot of energy as well. Today, we are not going to talk about processing near the sensor. We are going to talk about processing near memory or inside memory. So we will mostly focus on this part of the system, but many of the general ideas that we are going to discuss and cover today would apply as well to storage or sensors, or they could even apply to computing elements near the different SRAM-based memories that we have inside the chip. As I said, we are going to focus on processing in memory mostly, but processing in memory is not something new. It's not something that has just happened in 2023. As far as we know, is as old, I mean, it's like at least 50 years old or even more than 50 years old. And the oldest paper that we are aware of is this cellular logic in memory arrays from William Kautz, as you see, published in August 1969. 1 year later, this other one, 1970, a logic in memory computer from Harold Stone. And it's been a field of exploration for computer designers and for computer architects for many, many years, as I said, for all these decades. This is another example, more recent one from 1997, the research led by Dave Patterson, a case for intelligent RAM, which, by the way, was a paper that we discussed here in the seminar last semester. But why in memory computation today, and why not in the past? Why not in the 70s or in the 90s? Because there were important technology challenges that we are now more capable of solving. And also there is a larger need. Why is that? Because over the years, we have seen how memory improved over time, but not as fast as the processors themselves. As you may know, processors were improving for many, many years following Moore's law, doubling basically their performance every 18 months or something like that, while at the same time memories were improving, but not so quickly and not so fast. And that created a huge gap between the processing capability of systems and the memory and communication capability of systems. So there are a lot of problems with memory technology and with memory scaling. And these problems are related to the access to data, which is the main topic of today's lecture, but also reliability issues, such as the RowHammer example that I mentioned earlier. But at the same time, there is also a huge demand from applications and systems. I gave you the example in the beginning of recent neural networks, and you have seen how the storage needs of these neural networks has increased exponentially in the last few years. And that's basically what keeps happening, right? Applications are more and more demanding in terms of data, in terms of accessing data, and that increases the bottleneck, the amount of cycles spent on accessing data from memory and the storage, and the energy consumption that comes with that. And the designs are squeezed in the middle. So we need to come up with intelligent designs that can figure out solutions for the memory technology challenges, and at the same time, they provide solutions, they require tailored solutions for the modern applications. And all of this is possible because there are more and more innovations happening in the field of memory design and fabrication. One interesting example are 3D stack memories, such as, for example, the hybrid memory cube or the high bandwidth memory, HBM memory that you can find in many GPUs these days, or and also FPGAs and other accelerators as well. These sort of 3D stack memories consist of several layers of DRAM, and these layers are connected through some vertical connections that are called through silicon bias to a logic layer that is here represented by this bluish or purple layer, right? That's a logic layer, is not made of DRAM, it's made of CMOS logic. And there in the logic layer, we typically find buffers and controllers to access data that resides in the different layers of DRAM at low latency and high bandwidth. One good thing is that because this layer at the bottom is CMOS, it allows us to also embed some sort of processing elements there, such as could be, like, for example, specialized function units, or maybe general purpose cores, or many other potential compute elements. Automata processors from Micron are another example of processing near memory, but there are even more recent examples, and we are going to talk about some of them today. For example, UpMem, which is a French startup that is fabricating a processing in memory system that basically places some small processors called DPUs near the DRAM memory banks. We are going to talk about it later today. But that's not the only example, and companies already fabricating processing in memory systems. I mentioned UpMem, but also major vendors such as Samsung with their HBM pin memory is a HBM memory similar to the 3D stack memory that you see on the screen, that includes small SIMD processors near the memory banks in order to accelerate the AI and ML workloads. And SK Hynix, another major DRAM vendor, they are prototyping and probably starting to fabricate similar thing, but in this case, it's based on GDDR6 memory. And another example from Samsung, this one is a little bit different because it's DIMM-based solution. As you see, it's a normal DRAM DIMM, DDR6 DIMM, that places a small FPGA or reconfigurable fabric on top of the DIMM in order to compute closer to where the data resides. And this is another one, another example. I think we will have also a later slide as well. This one is from Alibaba, processing near memory accelerator for recommendation systems. But yeah, as I said, well, these innovations or innovations such as the ones in the previous slide, by the way, I mentioned here 3D stack memories, but I forgot to mention non-volatile memories as well, because most of the memory, the most dominant memory technologies is still DRAM, but we see more and more innovations as well in the area of non-volatile memories, and they can also enable processing in memory. And these innovations are basically trying to find ways of dealing with memory scaling issues. And these memory scaling issues are already happening for many, many years. This is a paper from Professor Mutlu from 2013. 10 years later, the landscape is not better, it's probably even worse. And another example that I gave you earlier as well, in terms of reliability and in terms of security, the RowHammer problem, it's also, like an important field of research for our group and for many other groups that are interested in making DRAM more reliable. You can check this paper from 2017 or more recent one, this retrospective published in 2019, or you can also watch some of the lectures that Professor Mutlu has delivered and delivers from time to time about RowHammer. For example, this tutorial or this also this story of RowHammer, 10 years since RowHammer was discovered. I think it's a pretty nice talk, and also in a very compact format, right? Just in 20 minutes, you can learn a lot about the RowHammer phenomenon and about other memory scaling issues. So, but as I was saying earlier, many of these issues can also be solved with intelligent memory controllers. So main memory needs intelligent controllers. Remember that when I mentioned earlier the RowHammer phenomenon, and I said you may have an intelligent controller that is able to identify when some memory request from a certain workload can represent a threat, right? Because they could cause RowHammer bit flips. If you have an intelligent controller, such as the one that Giray, one of the TAs of this course, and other people in the group presented a couple of years ago, this intelligent controller is able to identify when one specific application is trying to attack other applications by repeatedly accessing certain rows, and that way causing RowHammer bit flips. If your controller is able to do that, to identify those attacker programs, the controller can throttle the memory accesses, the memory request from this attacker, and this way protect other applications and protect the data that is used by other applications. This is an example of intelligent controller. Also, other examples of intelligent controllers you can find in emerging memory technologies, such as, for example, this phase change memory. This is a paper from 2009 that has received a lot of recognition and awards, as you can see, because it was really seminal in the development of or in the study of the PCM memory. This PCM memory, in fact, became a reality a couple of years ago or 3 years ago with the Intel Optane memory that you may have heard of. And it's not only research from our group, of course. Industry as well is writing papers about intelligent memory controllers. Samsung and Intel together presented this paper, co-architecting controllers and DRAM to enhance DRAM process scaling. So very interesting ideas as well in this paper. So the takeaway here is that we need intelligent memory controllers in order to avoid many failures and enable better scaling. So there are three key systems and application trends that I would like to highlight here. First of all, or just to summarize the many things that we are talking about today, data access is a major bottleneck because applications are increasingly data hungry. Remember this push from applications and workloads that are increasingly data hungry. Energy consumption is a key limiter, and data movement energy dominates compute. And that's especially true for off-chip to on-chip movement. Important, because we want to save energy and we want a more sustainable world. We want to avoid things like this picture. I think it's from Pittsburgh in the 20s of or the 30s of the 20th century. Hopefully we will never see this again, because we can build we can build computing systems that are high performance, but at the same time energy efficient and more sustainable. And this is a challenge for sure, but we also have very good opportunities for the future. So again, to summarize, data access is the major performance and energy bottleneck. And one reason for that is that the current design principles cause great energy waste and great performance loss. And the key reason for that, and remember the von Neumann model, is that processing of data is performed far away from the data. That's because data is typically kept in memory or storage devices, and we need to bring it back and forth from the memory and storage units to the compute units. So that's causes a great system cost, because all the data is processed in the processor, and we have seen multiple examples of these over the years. I would like to show you this plot from actually Professor Mutlu's PhD thesis, his run-ahead execution paper presented at HPCA 2003 for motivation. As you see, they showed this plot of LLC misses. I mean, not well, LLC, because I think that in this computer that they use the L2 was the last level cache. But as you can see, interesting observation here is that basically 55% of the execution cycles are spent on solving L2 misses, right? Yeah, this is the paper. If you want to take a look, you have links there. But the perspective has not changed in recent years. In fact, this is a much more recent study from 2015. It's a study from Google talking about their data center workloads. And one key observation here is that out of all the 100% execution cycles or pipeline slots, what we see is that most of them are due to this backend bound metric that basically represents the access to data. There might also be other causes for the backend boundedness, but most of them are due to the access to data. This methodology used here for the analysis called the top-down methodology. It basically divides the pipeline slots into 4 key values that represent either successfully used pipeline slots, the green ones, or different types of bottlenecks in the front end, in the back end, or due to bad speculation, for example, wrong branch predictions. As you see, well, most of the cycles are wasted, most of them due to the access to data, but for many other reasons as well. And if we look at the energy perspective, things are also not very optimistic here. Why is that? Because if you, for example, in this slide from Bill Daly used at High Peak 2015, one thing he showed, and this has not changed, it has not improved in recent years, is that the cost of performing a 64-bit double precision addition is basically 3 orders of magnitude cheaper than accessing the data, the necessary data from the memory. So as we can see, something between 2 times and 3 orders of magnitude, so 2 times and 3, no, 2 orders or 3 orders of magnitude more energy expensive to access data than operating on that data. For more motivation, you can also see this plot. That's from another paper from ISCA 2016. This is the energy for the y-axis represents the energy for a 32-bit operation, right? From an integer addition to a floating point addition, and access to the register file, multiplication of integers, floating point numbers, and then access to the SRAM or access to the SRAM cache or access to DRAM. You can see the huge difference, right, in this energy consumption just for 32-bit elements. Basically 640 times more energy consumption than floating point addition. So yeah, things are not going better over time. And remember as well, this figure that I showed you earlier, 62% of the energy consumption in mobile devices spent on data movement. So basically, the goal here is to try not to move data in order to save energy, a lot of energy potentially, and also execution cycles. Well, we need a paradigm shift to enable computation with minimal data movement, compute where it makes sense or where the data resides, and make computing systems more data-centric. And those are the key ideas that processing in memory or processing inside memory tries to exploit. We can see memory as an accelerator that is going to be somehow equipped with some sort of compute capability or processing elements. For now, you can think just about it as just as a small processor near the memory arrays. Later in this lecture, we are going to see many different types of processing in memory, but for now, you can think that way. And what is going to happen is that there will be a host processor, a CPU or a GPU, that will offload certain requests for computation to the memory. And at some point, memory will produce some results that will be moved back to the processor. That's how processing in memory systems are basically going to work. But in order to be able to design these kind of systems, there are many things that we have to redesign and think about. For example, how to design compute-capable memory, how to design intelligent memory controllers, how do we need to change the processor design or the communication unit design, how about the software and hardware interfaces, how do we program these new systems, right? And how to generate code for these new systems and new software. And of course, how much the algorithms and the theoretical foundations need to change, because as I said before, ideally, we will be able to co-design from the algorithm to the device and do it in a seamless manner and do it in an intelligent way in order to make compute systems that are much more energy efficient and high performance. For a thorough introduction to processing in memory, I can recommend you this reading, A Modern Primer on Processing in Memory. It's a book chapter that we wrote a couple of years ago, and it's publicly available and freely accessible in archive. And yeah, we will talk about several of the works that are presented in this book chapter. We are going to talk about them or introduce them in this lecture. But if you want to go deeper, and I will show you this slide later again, you can also take a look at the Processing in Memory course that we deliver every semester. We actually started it this morning. These are the links to the website and also the YouTube live stream from fall 2022. But as I said, we just started it today, so the spring 2023 edition just started. Now, the thing is, we want to create compute-capable memories. We want to design systems that handle data more efficiently. And in order to do so, we need to think differently from past approaches. Instead of considering memory as just a passive device that keeps just data and it's there for the processor, the CPU, or the GPU to go through the memory bus and request data from the memory, we can consider, or we should consider, that now memory can have the ability to compute in different ways. And that's what we are going to see today in this lecture from now on. But one way of changing our mindset with respect to memory is considering it not just as a passive device, but as an active device that can compute, that can behave as an accelerator. But how are we going to provide memory with this specialized compute capability? There are many different ways. And we are going to start dividing all these different ways into two different types, or two main approaches. These two main approaches are called processing near memory and processing using memory. I think processing near memory is easier to understand. As you can imagine, is going to consist of placing some processor near the memory. And that's why we are going to start with it. While processing using memory is a little bit more maybe sophisticated, also a little bit more far-fetched, but at the same time, probably even more promising, because it can enable much more throughput, it can enable much more, it can take advantage of the huge internal bandwidth of memory, and I believe it's a very promising trend for the future. So, where can you read more about these two PIM approaches? Of course, in the book chapter that I mentioned earlier, there is a section 5.2 that introduces these two approaches, processing using memory and processing near memory, and also provides different examples of enabling technologies for the two types of PIM. Okay, so I'm going to stop here. Are there any questions? No? Okay. Yeah, I still have a bunch of slides. I want to show you about 200 slides or so. Right now we are in slide 76. I know that this lecture may take longer than the official duration, but if that's the case and you need to leave, that's not a problem. You can go home and continue watching the lecture later, because we are live streaming it, and it will be in YouTube available for you to learn about this topic. Okay, I don't see any questions in the chat, in the YouTube chat, so I think I can continue. Okay, so let's start with processing near memory, and there is nothing better than giving a good motivation example to motivate processing in memory and motivate some approaches to processing near memory. We are going to start talking about graph processing. Graph processing is more and more important field of applications or algorithms, basically because graphs are everywhere and they are very much being used to, for example, understand what are the connections between users in social media and many other things. So graph processing algorithms are important for that, but graph processing algorithms, as we will see, have the problem that parallelizing their process is extremely costly and extremely difficult. And one reason for that, or the key reason for that, is the access to data. Here in the screen, in the bottom of the slide, you can see an example of what happens with performance when you increase the number of cores by 4 times. So observe that from 32 cores to 128 cores, the improvement that we can see in a hypothetical system, if you wish, is only 42%. So for 4 times more resources, we are only getting 42% more performance, which is basically terrible, right? And the reason for that are the basic characteristics of graph processing algorithms. Here on the screen, you can see the example of PageRank. PageRank is an algorithm, is an iterative algorithm where in each iteration, we are updating the rank of the successors of each of the vertices of the graph. And as you can see, it's a very lightweight computation in the end. It just requires 1 multiplication and 1 addition. But one problem is that graphs are huge, and also they are very regular. They are very sparse, because usually if you think about the users of a social network, each of the users of the social network may have different followers or friends or connections, but not everyone is connected to everyone else. And also the number of connections of each of us might change a lot. There are people who are very popular and they have many, many friends or many followers, while other people just have a few, right? And this makes that the graph itself is very sparse. And because it's very sparse, it's difficult to store it in memory in a regular manner that facilitates the access to the data. So it's also stored in memory in a compressed way, because we don't need to have useless information. There is no point in storing that I am not connected to certain people or to certain person, right? It's smarter to just store the information that is relevant, what particular people I am connected to, right? And that makes the graph very sparse. And that also makes that the memory accesses are very regular, or frequently random memory accesses. And because they are random memory accesses, they are more inefficient, because for one specific vertex, I may need to access here and later access here. And these two elements are not in the same cache line. What that means is I'm going to bring one entire cache line for one neighbor, for one successor, and another entire cache line for another successor, and maybe I'm going to use a couple of bytes or 4 bytes or 8 bytes of those entire cache lines, and that's costly, right? So that's one of the problems in graph processing. The other problem is that there is very little amount of computation. I'm bringing data from memory to just perform one addition or one multiplication or one addition and a multiplication, but in the end, it's not going to amortize the cost of bringing the data to the processor. So the opportunity is to use processing in memory to alleviate the data movement bottleneck in these graph processing algorithms. And we are going to give you, or I'm going to give you now a couple of examples that use 3-stack memories, processing in memory based on 3-stack memories to alleviate the data movement bottleneck in graph processing. The first one of the examples is the Tesseract system. This Tesseract system was presented at ISCA conference in 2015. And as you see, we can say that it's a coarse-grained accelerator that is connected to a host processor, for example, via the PCI Express bus. And as you see, this coarse-grained accelerator is composed of a number of cubes or stacks of 3-stack memory, each of them with their memory layers and with their logic layer. And as you see as well, these different memory cubes are connected in a certain way. There is a network to communicate from here to here. And what we are going to do with this accelerator is placing the entire graph or the entire amount of data that you need to process over the memory in all these different cubes. If we take a closer look at each of these cubes and we check what we have inside the logic layer, we identify this crossbar network that allows different computing elements to communicate. And then we also have these processing elements or computing elements that are basically small in-order cores. As you see from the in-order core, we can access the DRAM layers, and we can also communicate through the crossbar network with other cores in the same logic layer of the 3-stack memory. The Tesseract system proposes also for each of the in-order cores a few more components, like, for example, prefetchers to bring data early in advance from other parts of the same memory, or even from other memories in the same accelerator, or other memory cubes in the same accelerator. And it also has the ability to offload computation using remote function calls to other cores in the system. I mentioned prefetching earlier. So this Tesseract system was evaluated and compared to baseline systems using out-of-order cores. Like, for example, here, I think there are in total 32 out-of-order processors running at a frequency of 4 gigahertz and access to DDR3 memory. The second baseline replaces the DDR3 memory with HNC memory, which is like 3-stack memory, high bandwidth access from the host as well, but obviously not as high as if you operate inside the memory. And also a baseline that employs in-order cores, that many more cores, as you can see. These are some of the baselines that are compared to the Tesseract system. As you see here at the bottom, the aggregated bandwidth of the Tesseract system is way higher than the baseline systems, and there is where basically the key advantage of this Tesseract accelerator resides. And that's what we can observe if we check the performance, the speed up of the different versions of Tesseract. The fastest one is more than 13 times faster than the baseline of with DDR3 memory. And it happens the same if we look at the energy perspective here, more than 8 times energy reduction thanks to this accelerator that is designed, tailored for graph processing. Here you can find a link to the paper and also to the slides that were used to present the work in the conference. Remember as well, like To give you just another example, I mentioned computation near the storage earlier. This is a very good example of that. GenStore, a way of, I mean, it's an accelerator near the storage for genome sequence analysis. This basic idea of filtering out whatever information that is in the storage and I may want to potentially access, but I don't really need. Let's better do that computation near the storage because we are going to save a lot of energy and a lot of execution cycles if we don't have to move all the data from the storage to the memory to later process it in the CPU or in the GPU. Processing in memory is becoming real, and we are talking now about near memory processors or processing near memory solutions. And that these processing near memory solutions are the ones that are first appearing in the real world. In fact, you have already seen this slide before, but now we are going to talk with a little bit more detail about these different processing in memory, real processing in memory architectures that are already in the market, or if not in the market, they have been prototyped. I mentioned the AppMem company, this French startup that has fabricated the first publicly available processing in memory system. As you can see on the picture, these are conventional DDR4 DIMMs, but the key characteristic of these DIMMs is that inside each of the chips, there are not only DRAM memory arrays, but also small processors near each of the memory banks that are called DRAM processing units or DPUs. Here you can see another picture of these AppMem DIMMs, and as you see, they look like normal DIMMs, right? They look like normal DIMMs, but they are much more powerful because they have processors inside them. And we can use those processors. Of course, they are not going to work standalone. They are not going to work by themselves. They need to be controlled by a central processor, by a host processor, such as the dual socket CPU that you see in the picture. And this dual socket CPU still needs to have some conventional DRAM memory that keeps working as the main memory, as you can see here on the left-hand side of the figure. So there is still main memory, but we also have the PIM-enabled memory that now behaves an accelerator that has very large compute capability because there are many, many cores, 2,560 DPUs or 2,560 PIM cores or small processors near the memory arrays, and also large memory capacity, around 160 gigabytes of memory, of PIM-enabled memory that has this AppMem system. We have delivered multiple talks and multiple lectures. This is just one example lecture talking about the AppMem system. There are, in fact, more recent ones. Probably I have more pointers later in the slides. But let's take a closer look at this small processor and how it looks. The DPU, or the DRAM processing unit, is an in-order pipeline. The current generation, it runs at a frequency of 425 megahertz. So as you can see, it's pretty slow compared to a CPU or a GPU these days. But the advantage of this system is that it has many, many of these DPUs, right? It has more than 2,500 of these DPUs. So if you check the DPU pipeline, you'll see that in total, there are 14 pipeline stages. And these pipeline stages, I think it's pretty, as soon as you have a basic understanding of, or basic knowledge about computer architecture and in-order processors, you'll see that these pipeline stages are the typical ones for thread selection, instruction fetch. The instructions reside in that memory at the top that is called instruction RAM. So instructions are fetched from there. Then we need to access operands from the register file, format them, then compute using the ALUs, or also from these stages here, access SRAM-based memory that is this WRAM, a scratchpad memory that operates in a similar way as a software managed cache. and then result formatting, etc. This pipeline is a fine-grained multi-thread pipeline, and what that means is that we have multiple hardware threads. You might be familiar with the MIPS pipeline, for example, and you might have learned about pipelining, and maybe remember as well that there were some hazards in the pipeline whenever you need to use, one instruction needs to use data that is not yet in the registers or not accessed yet from the memory. You will need to stall the pipeline, or you will need to forward data from a later stage of the pipeline to an earlier stage of the pipeline. Nothing like that is available here, and it's not necessary because the pipeline is fine-grained multi-threaded. And what that means is that in every single cycle, we select, or the pipeline selects a different thread and goes to a specific program counter of this thread and to the specific instruction, fetches the corresponding instruction from the IRAM and starts executing it. So every single cycle, one new thread, and this avoids all hazards and potential stalls that we would need to have for correct execution. Observe as well that in total there are 14 pipeline stages, but we can have up to 24 we can use up to 24 hardware threads. So in principle, there are enough threads to keep all the stages of the pipeline busy, right? And this way, let's say, be efficient. And actually, one thing that we observe when we analyze this architecture is that the saturation point happens at 11 tasklets, 11 pin threads that are these tasklets or threads that run on the pipeline. This is our observation, and this happens for different data types and different operations. Here on the screen, you see integer 32, 64, floating point, and double precision floating point operands, and then you have results for addition, subtraction, multiplication, and division. We see that in all cases, the saturation point happens at 11 or more tasklets. So that's the minimum number of threads that we need to use in the pipeline of the DPU in order to get the maximum arithmetic throughput that these DPUs can provide. Another thing that we observe in our study is that there is a large throughput difference between integer data types and floating point data types. As you see, it's basically one order of magnitude. And the reason for that is that the DPUs are very simple. So their ALUs don't support floating point computation natively. They only support integer arithmetic natively. And floating point computation is emulated. So anything related to floating point operands is emulated. The runtime library calls a specific function that emulates and executes the addition of floating point values or multiplication or whatever. In fact, it happens the same as well for multiplication and division of integer values. And this is why we see this large performance gap between addition and subtraction and multiplication and division. So it's the pipeline is so simple that it doesn't even support 32-bit integer multiplication natively. But still, this system can be very beneficial for certain workloads. And I'm pretty sure that I have some results later, comparison with modern CPUs and GPUs, and you will see how much memory bound those workloads are for such a small processor and such a weak processor to be able to outperform a powerful CPU or a powerful GPU. We did very extensive analysis of this UpMem PIM architecture, and well, we characterize the arithmetic throughput as you have just seen in the previous slides, but also the bandwidth that we can obtain with the system, and the bandwidth, the overall bandwidth is pretty large. In our measurements using the stream benchmark, we observe almost, well, more than 600 megabytes per second, and this is for one individual DPU. So that means that if you have a system with more than 2,000 DPUs or more than 2,500 DPUs, the overall aggregated bandwidth is around 2 terabytes per second. That's larger than even the most powerful GPUs that you can find right now in the market. The NVIDIA A100, for example, has a bandwidth of 1.5 terabytes per second. Probably the next generation of NVIDIA GPUs will double that bandwidth, but I hope that future generations of pin systems will also increase the bandwidth significantly. One observation here, you can read this banner later more carefully, but one observation here is that some workloads, for some workloads, not many, but for some workloads, we see that the saturation point happens before 11 tasklets or before 11 pin threads. And that's basically because those workloads are memory bound, even in these DPUs. But observe what workloads are we talking about? It's copy and add. Copy is just copy. There is no computation at all. We are just copying data from one part of the memory, the DRAM bank, to another part of the DRAM bank. So to do that operation, we can do it at maximum bandwidth without using more than 4 or 6 tasklets. In the add version of the stream benchmark, what we are doing is reading elements from 2 arrays, adding them and storing in a third array. So we are reading 2 elements and writing 1 element just for a single addition. So there is a lot of data movement, and that's why we also see a saturation point happening with less than 11 tasklets. But as soon as we do something a little bit more complex, like in scale and triad, in scale we use multiplication, and remember that multiplication is emulated, so it takes more cycles, might take up to 32 cycles for 32-bit integers, or triad that uses multiplication and addition. Now we start saturating at 11 tasklets. And the reason for that is because the latency of the pipeline, the latency of executing instructions in the pipeline is hiding the latency of the memory accesses. Remember that we are talking about a single DPU as accessing a single memory bank that is nearby, and notice that with just as little computation as only 1 multiplication or 1 multiplication and 1 addition, we are already saturating the pipeline throughput. We are already hiding all the memory accesses, and basically the workload is compute bound. If you think about how a workload like scale of triad behaves on a CPU or on a GPU, you will see that it is extremely memory bound. But now things have completely changed here. We have flipped the coin completely. So as I said, we have a lot of experience, and we have done a very extensive analysis of this UpMem PIM architecture. This is one paper that we published first in archive, later in one journal, and some key takeaways of our work. First of all, something that I just told you, that this processing in memory architecture is basically a compute-bound architecture, because very quickly the workloads are going to fall into this compute-bound region. So most typically real-world workloads are going to be on this area where the performance is basically determined by how fast the pipeline is in processing arithmetic instructions. This is the first key takeaway. Another key takeaway, and this comes from the comparison to CPU and GPU, is that because the processors are not very powerful, the workloads that are more suitable for this processor, for these DPUs, are those that don't require many arithmetic operations or use only very simple arithmetic operations, ideally integer operations and addition and subtraction that are faster. But you can see here the comparison to CPU and GPU for different types of workloads. The ones on the left are those that we call more pin-suitable workloads, because the larger pin system, that one with 2,500 DPUs that we use, outperforms the state-of-the-art GPU. In this study, we use an NVIDIA Titan 5 that is like maybe 2-3 years old, and observe that well, the larger pin system can outperform the CPU and the GPU for important workloads such as the transposition, scan operation, reduction, histogram calculation, binary search, select and unique, that are database operators, etc. But as soon as you have a little bit more complex computations, such as, for example, these SPMB, sparse matrix vector multiplication, or simple dense matrix vector multiplication, or a multi-layer perceptron neural network, or bioinformatics algorithms like Needleman-Bunch, we start observing the bottlenecks that obviously this system suffers as well. Basic idea of our study, and this comparison to CPU and GPU, was to understand the pin system and understand what workloads are more suitable for this pin system. I already said before, key takeaway number 2, workloads that don't have very complex computations, they don't use floating point operations, ideally not even integer multiplication or division, but also another important thing is that ideally these workloads also don't require much communication between different pin processors, between different DPUs. And the reason for that is that there is no direct communication channel between different processors, even pin cores, even if they are in the same chip. That's one clear limitation of this pin system. It's something that we can also expect as well, basically because it's the first generation of this pin system, but I'm pretty sure that in future generations, we will see a different behavior. I mean, we will see improved performance for sure. In this case, takeaway number 4, I'm just showing you some summary of our observations in comparison to CPUs, comparison to GPUs. As you can see, well, in the comparison to CPU, the larger pin system was faster than the CPU for 13 of 16 workloads that we evaluated. In the comparison to the GPU for 10 out of 16 workloads that we evaluated. And in terms of energy efficiency, we observed similar trends. Whenever as the pin system is able to outperform the CPU or the GPU, it will also be more energy efficient. You can learn much more by reading the long paper, or this one is a shorter version of the paper. And you can, in fact, access all our workloads, benchmarks, and micro benchmarks from the public repository. This is the entire list of workloads that, well, some of them, I mentioned them earlier when we were analyzing the results, but these are they are called the PRIM benchmarks, and they, as I said, publicly available in our repository. And many more talks where you can learn more about this architecture, like this one, or this one, or this one. And the lectures in our processing in memory course as well, and the later works that came after the initial analysis of the architecture. For example, these 2 papers focus on machine learning training on a real processing in memory system. This is a more recent work that where we here implemented 4 classic machine learning algorithms: linear regression, logistic regression, decision tree, and k-means for the UPMEM PIM architecture, and basically analyzed the system and came up with some observations about what are potential optimizations that we can apply to our algorithms to make them more suitable to this pin system, and we were able to observe interesting performance improvements with respect to the CPU and the GPU for at least 2 of the algorithms. So you see, in this case, we even compared to a more recent GPU, an A100, and for one of the algorithms, for k-means, the pin system is like 3.2 times faster than the A100 GPU. There is also a recent talk about this work as well. And it's not the only one. Sparse matrix vector multiplication, which is extremely important operation for many different applications. There is a recent work from us as well, this sparse P library, where we studied many different implementations of SPMB on the UPMEM PIM architecture. In total, 25 different versions of SPMB using different compression approaches, data types, data partition and synchronization, and load balancing approaches, like really comprehensive work and really comprehensive analysis to understand why this specific operation performs better or worse on this UPMEM PIN system. If you want to learn more about the sparse P library, there is a link to a lecture delivered by Cristina Gianola, who is the first author of the sparse P paper. So this is with respect to the UPMEM pin system, but as I said, UPMEM is not the only company that is designing and fabricating processing in memory systems. Samsung, 2 years ago, exactly 2 years ago, announced HBM PIM, a processing in memory architecture targeted at AI and machine learning. I think I mentioned it earlier. It's something like this. Remember, 3D stack memory, multiple layers of DRAM on top of some logic layer buffer die called in HBM. What Samsung did with this function in memory or FIMDRAM or HBM PIM, now more recently they are calling it HBM PIM, is that they modified some of the layers, these 4 different layers at the bottom. They modified them to embed some small processor inside, near the memory banks, in between one computing block or PCU block in between 2 memory banks. How do these PCUs or programmable compute units look like? Observe that they also have a pipeline that is different from the pipeline that we have seen for the UPMEM PIM architecture, and is different basically because this one is more specialized for specific operations, multiplication and addition, as you can see in the pipeline. Why is that? Because this architecture is intended to accelerate machine learning and artificial intelligence, and multiplication and addition are key, at least in the current machine learning and neural network models that we are using today. So they are key, and we also perform this multiplication and addition in parallel because these arrays are in reality SIMD units that can operate on 16 operands at the same time. Observe as well that these ones don't have any issue with floating point. In fact, they are native 16-bit floating point. They can natively handle 16-bit floating point values. And well, you can see the rest of the components of the PCU, this register group with different types of registers, some of them for instructions, for data coming from the memory bank. Notice here at the right-hand side how we have a bus to the even bank and to the odd bank, because there is one PCU block in between 2 of the memory banks. And they also have their instruction set, as you see, is more restricted, as I said, than the instruction set of the UPMEM PIM architecture that is more general purpose, but there is a good reason for that, as the title of the paper says, for machine learning application, right? And here you have a picture or a photo of the chip itself. Well, this is like one of the layers of the 3D stack memory, and observe how we have these PCU blocks in between an odd and an even numbered bank. The other proposal from Samsung that I also mentioned in the beginning is this AXDIM. It's a DDR-X PIM, is a DIM-based solution. As you see, it's a regular DIM that places some small FPGA in the middle of the DIM, and this FPGA can have 2 processing elements, at least 2, to be able to access the data from the 2 ranks of chips that the DIM contains. And they also showed pretty interesting results for deep learning recommendation systems. And another, this one is more recent, presented exactly 1 year ago by SK Hynix, the accelerator in memory, or AIM, also basically targeted to machine learning, high performance computing, etc. And it resembles as well the design from HBM PIM, because as you see, processing units near the memory bank, in this case, is 1 processing unit per memory bank. But if we look closer and we look at the processing unit itself, you see that again we have an array of multipliers and then another 3, because what we want to compute here is multiply and accumulate operations and dot product operations that are the key operations for matrix multiplication or matrix vector multiplication, that are the key primitives in most neural networks these days, right? There are a couple more interesting innovations in this same architecture, for example, that they include some logic and some lookup tables in the memory banks to perform activation functions that are needed as well for the execution of neural networks. And something that I like as well is that they have this supplementary SRAM buffer in the chip that can be used to move data between different memory banks and to communicate data across processing units. I think it's a pretty interesting innovation as well. And I mentioned as well this design from Alibaba. This one is focused on recommendation systems. As you see, they've used a different fabrication technology as well. It's called hybrid bonding. It basically consists of two different dies, two different layers. One is DRAM, the other one is logic. As you see, DRAM is composed of multiple memory banks, and the logic layer contains so-called neural engines and match engines that are used for the recommendation system. Interesting innovation in this processing near memory engine from Alibaba is that they use this hybrid bonding technique, that is the fabrication technique to glue the two layers and connect them together tightly in order to enable and to allow high bandwidth between the logic layer and the DRAM layer. So these are the examples of processing in memory in the real world, systems that are already being commercialized or have been prototyped and hopefully will be commercialized pretty soon. The most recent thing I know, for example, from Samsung is that they integrated their HBM pin memory into AMD GPUs. And after that, they were performing experiments for different networks and basically observed 2 times performance improvements and 2 times energy savings with respect to a plain AMD GPU with HBM memory, but not PIM-capable HBM memory. So as you see, the future is pretty promising for all these systems and in these directions. But yeah. Yes. Hello?
There is a question in Zoom. Sven,
okay.
if you can ask directly.
Yeah, sure. So as I understand that is most hardware is enables PIM and PAM is designed for special purposes like machine learning or graph processing. But you mentioned that there is at least some DPUs that can get machine instructions from the CPU. So is there a way, or is it possible in the future maybe that these can be used for general purpose machines like PCs, for example?
Yeah, I think so. I don't think that the PIM paradigm is restricted neither to any specific device nor any specific type of applications. What we can see so far is that I mean these initial experiences in the real world from different vendors, they are either focusing servers, because in, like, for example, is the case of AppMem, right? Where what they can sell you is a relatively large server with multiple DIMMs of conventional DRAM and PIM-enabled memory, and that makes sense because if you are going to invest on a new system, it's probably something that you want to use for many workloads in your company or in your institution, right? So I think it makes sense for them to start at the server grade product, let's say. But if you think about the workloads, it also makes sense. I think it also makes a lot of sense what Samsung or SK Hynix are doing, designing and fabricating processing in memory systems that can accelerate what are probably the most important workloads these days, right? Or where most people in academia and industry are putting their attention, that are machine learning and neural networks.
Okay.
But that said, I think processing in memory is promising for any sort of workloads as long as they are truly memory bound, and also all sorts of devices. And observe that one key advantage of processing in memory is that it can save a lot of energy, and that's especially important when we are talking about mobile devices like cell phones or laptops, etc.
All right, thank you.
Yeah, thank you for the question. Okay, so I was saying, if you want to learn more about all these different processing in memory systems, my recommendation is that you check the lectures in our processing in memory course. As you see, we have the dedicated lectures for each of the recently presented systems and prototypes. So now we go to the second part of these processing in memory approaches, processing using memory. In processing using memory, as I said before, is a kind of a more futuristic solution. I would say that there are no processing using memory systems that we can buy these days, but there are some prototypes already, academic prototypes mostly, and in fact, we can use them for research already. But let's start simple, and let's start thinking about use cases where these processing using memory approaches can be useful. One way of using processing using memory would be data copy and initialization. Why do if I just want to copy data from this part of the memory or to this part of the memory, why do I need to move the entire chunk of data to the processor, bring it to the processor, to the L1 cache, and then move it back to the memory? That's extremely costly, right? That as we are going to see, in fact, in one example. But that simple operation that you may think, well, we are not always doing that. It's true, we are not always doing that, but recent study from Google showed that 5% of the cycles in Google's data centers are spent on mem-move and mem-copy operations, and 5% of the cycles in a data center is a lot, right? And it's a lot of energy consumption. If you think about future PIM systems, as I said, instead of having to bring this whole wide region near to the processor and then back to the memory, ideally, what we could do is just something like this. And that's going to be low latency, it's going to save bandwidth, it's going to avoid cache pollution because we are not using the cache at all, and it's avoiding unwanted data movement. And if you compare what's the cost in latency and energy of copying the data through the CPU, through the processor and the deep cache hierarchy, compare it to the latency and energy consumption of an operation like this, you'll see that we can potentially reduce both latency and energy by 2 orders of magnitude. And it can be something as simple as the row clone operation. You probably remember how DRAM works, right? If we want to read something from DRAM, first thing we need to do is to activate one of the rows, and then we activate the row buffer. So what that makes is that we transfer the entire row from its original location to the row buffer. And after that, we can start reading bits, individual bits, or chunks of 8 bits from the row buffer. We can read or write, right? By simply modifying a little bit this process, we can copy rows inside the same DRAM subarray. First, we need to activate row A, then we activate the sense amplifiers in the row buffer in order to transfer the row to the row buffer, and then we activate the destination row because we have all the contents of row A in the row buffer. If we now activate the destination row B, we will copy the entire row directly to the destination, right? So this is as simple as issuing from the memory controller 2 consecutive activates and at a negligible hardware cost, and potentially with great improvements in terms of latency and in terms of energy savings. This is the row clone paper. This was presented in Micro 2013 as an efficient, fast and energy efficient way of performing bulk data copy and initialization. Of course, we can also do initialization, either all zeros or all ones, or maybe a pattern of zeros and ones, as long as the source row is like fixed rows of either zeros or ones or any other pattern. And and one thing that you may ask yourself is, if this is so simple and so efficient, why it doesn't exist yet in the real world? And that's really a very good question. Of course, there are challenges that would need to be solved as well before doing something like row clone ubiquitous in real systems, because memory uses I mean, in computing systems we use virtual memory that we need a memory address translation from virtual memory pages to physical pages, and the way that data is mapped onto memory is done on a specific way that we may not know. Maybe it's maybe even hidden by the DRAM vendors, or more challenges that there might be related to the fact that we have virtual memories that from time to time pages are swapped out and they may be moved to the storage. So there is no certainty in some cases of whether one page is in DRAM or not. Of course, there are challenges to enable these sort of techniques, but what has in fact been shown by recent research is that it's even possible to perform this operation in off-the-shelf DRAM chips. These folks from Princeton University in 2019, they showed that by violating DRAM timing parameters, they were able to mimic row clone, and they were able to activate two rows, sending two consecutive activates to these two rows and copy one from the contents of one row into another row, and do it. And they were able to do it for some chips even with high reliability, with 100% success or almost 100% success. And in order to study all the challenges that need to be solved in order to enable a technique like row clone, we in our group developed this PyDRAM framework that is an FPGA framework that it provides an end-to-end system, sort of a playground to evaluate processing in DRAM techniques such as row clone. You can read the paper. You can also even access the code from the repository if you want to implement this on your FPGA. As you can see here, I mean, this is the prototype with an FPGA board. Inside the FPGA, we implemented a CPU core, a RISC-V CPU, and from this RISC-V CPU, we can send, for example, row clone commands to the PIM-enabled DIMM. We are calling it here PIM-enabled DIMM, but it has nothing to do with AppMem DIMMs or something like it's truly processing in memory DIMM. In reality, we call it PIM-enabled DIMM, but it's a conventional DDR3 DIMM where we were able to activate two rows in the same subarray in order to two rows back to back in the same subarray in order to perform this row clone operation, but all of that commanded by the RISC-V system in the FPGA. You can read the paper and you can access the code for the FPGA and the entire system in the repository. And just to show you some experimental results that we obtained with this prototype, this is the throughput improvement of doing the in-DRAM copy and initialization using row clone or using the regular RISC-V CPU. You see, well, more than 100 times throughput improvement when using the processing in memory technique itself. This is the link to the repository, link to the paper, and also Ataberg, who is the first author of this work, has delivered several talks about this work, such as this one, for example, from fall 2021. Row clone is not the only way of doing processing using memory, and in fact, it's relatively limited because it's only super efficient when we are moving data inside the same DRAM subarray. Later research work has proposed ways of doing fast inter-subarray copy from one DRAM subarray to another DRAM subarray. That's the LISA paper presented in 2016, but also data movement at smaller granularities. For example, the Figaro paper presented in Micro 2020. This, just to give you an example of these different works, LISA, what LISA basically proposes is to connect different DRAM subarrays using simple isolation transistors that connect the bit lines from one subarray, from subarray 1 to subarray 2. And when we activate these isolation transistors, we can perform something similar to the row clone operation. Copy an entire row from subarray 1 to subarray 2. And that's this row copy, or this fast bulk data copy, is not the only application that LISA provides. If you check the paper, you'll see other applications such as DRAM caching or fast pre-charge. Yeah, but you can find here links to the LISA paper. This is the other one I mentioned, Figaro, improving system performance via fine-grained in DRAM data relocation and caching. In this case, it's the global row buffer and the global links that connect different subarrays inside the same bank that are being used to move data from one subarray to another subarray in a fine-grained manner, or also this other proposal that is based on 3-stack memory, integrating a network in the logic layer of the 3-stack memory. This is with respect to copy, but it's not the only thing that we can do using memory. More recent work showed that we can take advantage of the analog computation capability of DRAM and perform bitwise operations, things like AND, OR, NOT, majority, by activating multiple rows in DRAM at the same time. We are able to perform these operations. And by the way, these operations have already been shown possible by the authors of this Compute DRAM paper in some real chips. We will probably see more research in this direction in the future. This multiple row activation was proposed in a paper in 2017, and I'm going to describe it briefly for you to understand it and for you to understand what are the true potential of these techniques. By the way, this sort of computation, this analog-based computation, is not only possible in DRAM, is also possible in other memory technologies, like non-volatile memories like memristors, resistive RAM, phase change memory, STT-MRAM, and there have been several works from academia that have shown that after the publication of the row clone and bit paper, and all operate on data with minimal data movement. But let me very quickly explain you the basic idea of this triple row activation. Imagine that we have 3 rows inside the same subarray. Now here we are representing only 3 cells, A, B, and C are in different rows. These 3 cells are connected to the same bit line, right? And hence connected to the same sense amplifier that we have here. Notice that the capacitors of these 3 cells, 2 of them are charged. The third one is fully discharged. If we activate the 3 capacitors, if we activate the 3 rows at the same time, what happens is that the 3 cells start sharing their charge with the bit line, and this causes a perturbation in the bit line represented by this delta that you see there. And then when we enable the sense amplifier, what happens is that whatever perturbation we have on the bit line is going to be amplified. Now think, what we have the most? Do we have charged cells or discharged cells? Because we have 2 cells that are charged and 1 cell that is discharged. What happens when we enable the sense amplifier is that the bit line goes to BDD and the 3 capacitors end up being charged. Now, if you observe the operation that is really happening here, this is called a majority function. That basically means that if we have 3 cells, 2 1s and 1 0, the result will be 1. If we have 2 zeros and 1 1, the result will be 0. That's a majority operation. Using this majority operation, we can implement either or AND. It all depends on what's the value of one of the 3 cells, fixed to 0 or 1. If it's 1, we will have AND. If it's 0, we will have, no, the other way around. If it's 1, we will have OR. If it's 0, we will have AND. For an example of how to use this bulk bitwise and or, what we would do is copying using row clone for sure, copying rows to some designated rows that are rows that can be activated, the three of them at the same time, due to a specialized row decoder that is proposed in this in the paper. We activate the three rows at the same time. We obtain the AND operation in the entire row, right? That's why we call it bulk and then we can store the result into the destination array. This was first proposed in a CAL paper in 2015, but later the design was improved with a way of performing the NOT operation as well. Because now if we have AND, OR, and NOT, we have a functionally complete set, and with this functionally complete set, we can perform any other more complex operation, as you know. The basic idea for the NOT operation is that in each DRAM subarray, we integrate one so-called row of dual contact cells. As you see, the dual contact cells have two access transistors, and the access transistor at the bottom is connected to the bit line bar. It's connected to the other side of the sense amplifier, the other side of this inverter. So whatever value we have on the bit line is inverted on the other side. And when we activate this access transistor that we have here, the negated value will be copied into the cell. That's a basic idea. There could be other ways of doing NOT. This is the way that the AMBIT paper proposed. You can check the paper for many results, but yeah, some of them are here. I think like very interesting ones. If you compare AMBIT and AMBIT 3D to other devices like the Skylake CPU or NVIDIA GTX 745 GPU, we see basically 2 orders of magnitude performance improvement, at least in terms of performance and also in terms of energy consumption. And the AMBIT paper also showed how to apply these bulk bitwise operations to different workloads. For example, the bit weaving workloads for database queries, something between 4 times and 12 times performance improvement for this specific application with respect to a CPU with SIMD units. You can check more details in this AMBIT paper or in this later book chapter, or in the more recent SIMDRAM work that we published in April 2021. SIMDRAM proposes an entire framework to implement complex operation using these processing using DRAM techniques. I'm going to very briefly explain it, and after that, I think we'll be mostly done. I think it's interesting because you are going to understand how it's possible to make use of DRAM and this triple row activation to compute complex operations such as additions, multiplications, or basically anything else. The SIMDRAM framework, as you see on the screen, proposes 3 steps to create these complex operations by just using activate and pre-charge commands that activate the 3 rows simultaneously, or can be used as well to copy data from one row to another row, right? Remember as well, we all know, or you all know here, that with AND, OR, and NOT, you can represent any desired operation. For example, this one here is an addition, is a bit, an addition implemented with AND, OR, and NOT. And that's something that we all know and understand pretty well. But something that maybe is not so much well known is that majority and NOT, the majority logic function and NOT together, are also a functionally complete set. So we can also implement addition or anything else using only majority and NOT. And now remember the AMBIT proposal. We can have AND and OR using DRAM, but what we are basically doing is activating 3 rows, and in the end, obtaining the majority result. If we have 2 ones, the result will be 1. If we have 2 zeros, the result will be 0. By just using majority and NOT, we can same as with and or not, we can create any complex operation. So the very first step in the Sindiran framework is to convert the and or not representation into a majority not representation. And once we have that, we should be able to generate the sequence of DRAM commands. With one activate pre-charge, for example, we can perform a majority operation. With the first activate, we activate 3 rows at the same time. With the second activate, we copy the result to a new row. That's what Ambit proposes, and that's what we are using here. The only thing is that in step 2, we need to figure out what's the sequence of DRAM commands that we need to issue for whatever logic we want to compute inside memory. And this sequence of commands is later organized as a microprogram that will be executed by the memory controller. The memory controller is enhanced with certain control units and certain kind of FSM that is able to read the microprogram and send the required commands to the chip in the DRAM DIMMs, and this way perform the Ambit or SIN-DRAM operations. I think I already explained this first step, second step, third step, and now if you want a little bit more detail, we have it in these slides. Remember, an AND is a majority where one of the inputs is fixed to 0, and OR is a majority where one of the inputs is fixed to 1. Remember as well that Ambit supports a majority natively. That's what it basically supports. So in the first step of SIN-DRAM, what we do is converting this and or not representation into a majority not representation. We first do the, say, naive transformation, just replacing each and or with the corresponding majority with a 0 or a 1 as the input, but this leads to an optimized circuit. Later, we can apply further optimization steps using a greedy optimization algorithm that was proposed in this paper from 2014, and this way can have a optimized circuit based on majority and not. Once we have that, we go to the second step, and in this second step, we need to generate the microprogram. The basic idea is first to allocate the operands to the DRAM rows and then generate the microprogram itself. So in order to allocate the rows, to allocate the operands, we need to understand how we need to know how the subarray, the DRAM subarray is organized. I mentioned this earlier. We cannot use all rows in the subarray to compute, just a few ones. Well, ideally, we could have a much more complex row decoder for the entire subarray, but the authors of Ambit propose just a small decoder that is able to activate 3 rows, but only, let's say, a limited set of rows can be activated by these special row decoders. So that's why we need to do, first of all, a row clone operation from the regular rows to the compute-capable rows, and then we will activate 3 rows at the same time. So this is more or less how it works. So when it comes to allocating the operands to the DRAM rows, we have to take into account, and we have heuristics for that, or a data placement algorithm for that. We have to take into account what's the sequence of operations that we need. And we need to take into account certain constraints that the substrate imposes. The first one, I just mentioned it, there is a limited number of rows that can be used for computation. Second one is that rows have, the triple row activation operation has a destructive behavior. Because if I have here 0, 0, 1, after activating the 3 rows, in the end, because the majority result is 0, the 3 cells will contain a 0. So I'm destroying the original values, the original bits there. And that's also something to be taken into account when performing the allocation of operands to rows. The thing is that, we can perform this allocation, for example, for that simple majority operation that is part of a full adder, and actually is what we need to calculate the carry out. We could directly place A, B, and C into the compute rows and then activate them, and this way we have 3 copies of C out. And this can be useful, by the way, because now we have 3 copies of the same operand, and we can use them in later operations. They can be reused. After we have the data placement, we generate the microprogram. For example, what do we need here? Well, we may need to first copy using row clone from row A to a reserve row to a compute capable row, then copy B, then copy C in, and then execute the majority operation, right? This is the microprogram. And observe that the microprogram is basically composed of activate and pre-charge operations that are 2 of the basic commands that DRAM controller sends to the DRAM chips. And then we can copy the destination. This could be the initial microprogram. It's also possible to apply certain optimizations, like, for example, coalescing row copies. I'm not going to enter into the details here. You can read the paper for more details. But the thing is that we can optimize this microprogram as well, and also save, activate, and pre-charge commands in some cases. And then we have to take into account that operands are usually more than 1 bit. Because if we want to do a 8-bit addition or a 32-bit addition, we will need to repeat this process as many times as bits we have in our operands. So that's basically a step 2, where we generate the microprogram, and in step 3, we just use the control unit to receive one SIMDRAM instruction from the SIMDRAM enabled application. This is the host code, right? And there are some new instructions that we design. When the pipeline finds this instruction, sends it to the memory controller, the memory controller will grab the corresponding microprogram and will start sending activate and pre-charge commands to the DRAM chips. By doing so, you can have a very high throughput machine, SIMD machine. We call it SIMD because with a single instruction, we are operating on multiple data elements at the same time. And now we can consider that each of the bit lines in DRAM is like a SIMD lane in a SIMD processor. But instead of having 16 or 128, we have thousands or even millions of these SIMD lanes. And this is well, a picture of the SIMDRAM control unit. You can find many more details in the paper, many more details in the paper about, for example, system integration, how to transpose data is something that I didn't mention earlier, but something necessary, because observe that we are operating on individual bit lines, right? So instead of placing data and operands in a horizontal manner, as we normally do, we need to transpose data and have entire operands in the same bit line, right? If you want to add element A0 and B0, we need to have all bits of A0 and B0 in the same bit line. That's one of the challenges for the integration of SIMDRAM in real systems, but hopefully we will find solutions in the future to do so. And actually the paper proposes a way of transposing data. You can check later. And here, just very quickly, you can see some performance and energy efficiency results with respect to CPU and modern GPUs. And this is the paper. So it's not the only thing that we are doing, and other groups as well are doing in terms of processing using memory or processing using DRAM. We can also use memory to directly generate random numbers or also physically unclonable functions, as this paper that we have discussed sometimes in this course as well. This one is similar approach, but in this case to generate true random numbers. More recently, we presented this one Quack TRNG that takes advantage of the fact that multiple rows can be activated in commodity DRAM chips, and in this case, it opens 4 rows at the same time. Imagine we have been talking all this time about majority, right? Majority requires ideally in a majority function, you're going to have an odd number of inputs, right? Like 3 or 5. But what happens if you have 4? You have 2 zeros and 2 ones. You don't know what's going to happen, right? So that's the basic idea. You don't know what's going to be the result. It's going to be kind of random. And that's what the Quack TRNG paper shows. You could potentially no. In reality, because they showed it for real chips. You can activate 4 rows at the same time by violating the internal DRAM timing parameters, and this way generate random numbers. This other paper, the Dr. Strange presented an end-to-end system for true random number generation. And I mentioned earlier that these kind of processing using memory techniques are also in other types of memory. I mentioned memory stores, ReRAM, etc. This is a recent work where we showed that this can also be done in NAND flash memory chips. Or this other one that also extends the ambit work, but in this case to provide a way of doing lookup table queries inside DRAM, and this way also save a lot of increased throughput, and it's also a very interesting way to implement complex operations. So these are the 2 key trends: processing near memory and processing using memory. There is still a lot of work to do in order to enable processing in memory in real systems, and these are potential barriers. We are not going to cover them in detail, of course, but I mean, different barriers that need to be solved relate to how to program these systems, what type of applications are good for them. We obviously need to generate new software, or at least find ways of compiling existing software into these new devices. We need to take into account system and security considerations such as coherence, synchronization, virtual memory, isolation, runtime and compilation systems that help us in doing, for example, the data mapping. Remember, we just talked about how to allocate operands to DRAM rows in DRAM, but also the adaptive scheduling. When does it really make sense to offload computation to PIM, or when makes more sense to compute on the processor, maybe because the cache lines that you want to operate on are already in the cache, etc. And also infrastructures as well, like benchmarks, for example, or simulators. But all of this can be solved with a change of mindset that spans the entire stack, and we can get there step by step. And we have the opportunity to build fundamentally energy-efficient data-centric computer architecture, fundamentally high-performance computer architecture, and basically computing architectures with minimal data movement. Some concluding remarks here: we must design systems to be balanced, high-performance, and energy efficient, all at the same time. These are intelligent systems that are data-centric, data-driven, and data-aware, that enable computation inside memory or close to the memory or using the memory, and this can lead to a lot of performance improvement, energy savings, and enable new applications and new compute platforms, and even enable a better understanding of nature and many more things. So the future is bright for truly memory-centric computing systems. Oh, wow. And now I don't know the password. Okay. Thank you, Yahya. Okay, so yeah, well, this is the future, and we expect that these memory-centric computing systems will become a reality, or will continue becoming a reality very soon. Fundamentally better architectures that are data-centric, data-driven, and data-aware, and maybe someday as nice and well-designed as our own brains, right? But yeah, definitely we need to revisit the entire stack and exploit good principles in the design of these data-centric systems with intelligent components, better communication and better interfaces, better designs, heterogeneity as well. By the way, we have another course about heterogeneous systems that is starting tomorrow at 9 a.m. Heterogeneity as well, because different types of workloads require different types of computing elements and different types of memories as well. So that's why heterogeneity is important as well. And of course, being flexible and adaptable. But that requires to be probably more open-minded that some people are still are. If you want to learn more about processing in memory, for sure, we are going to cover more than one paper related to our processing in memory research in this course. But remember, the book chapter is clearly a good recommendation for your reading. But if you prefer to watch lectures or talks, we are frequently organizing special sessions, tutorials, courses, etc. This is, for example, a link to a special session that we organized last year in July as part of the VLSI symposium. We are, by the way, this week, we are premiering in YouTube some of these talks, as you see. I'm not exactly sure what's the one happening tomorrow, but as you see, there are still a few of them that are upcoming. You can find many more materials in our processing in memory course and also in the computer architecture master course that Professor Mutlu taught in the past fall semester. Even more publicity, this is a recent tutorial that we delivered in the HPCA conference a couple of weeks ago, HPCA 2023, an entire day of lectures, not only from us, but also from other people in academia and industry. We had two interesting talks, one from IEDM, the other one from Alibaba, and you can access all the materials in the website and the recording from there. And there is one more tutorial, the second edition of this tutorial, where we will have, for sure, new contents and new talks that will happen again in ASPLOS 2023 on March 26th. This will happen on site, but we will also live stream it. So yeah, if you are interested, you can attend remotely or on site as well if you wish, and or watch the lectures later. So this is all from my side. It took 2 hours, 3 minutes in total, I think. So yeah, thank you very much for your attention. If you guys have any questions, please let me know, or you can contact me later. Anything? Okay, are there any questions in YouTube or Zoom or something? No, I don't think so. Okay, so then we are done. Thank you again.